For my Lab 5 experiment, I decided to attempt to find the spring constant of the trampoline in my backyard and verify that the energy principle applies in situations involving masses bouncing on the trampoline. To do this, I observed the bounce of a pool ball caused by the trampoline being stretched to a known distance to find a value for the spring constant. Then I used this value to observe the motion of a basketball bouncing on the trampoline. Ultimately, I found that my trampoline has a spring constant of 105.37 newtons per meter, and while situations on the trampoline do adhere to the energy principle, there were significant discrepancies between position data generated by my experiment and position data produced by my computer model. The fundamental principles used in this lab were the energy principle and Newton's second law. When using the energy principle, the system in consideration was the ball that bounced off the trampoline, as well as the earth and the trampoline itself. When observing motion with Newton's second law, the system in consideration was just the bouncing ball. Here is tracker footage of the bounce of a pool ball that was generated by stretching the trampoline a measured distance. In this situation, the origin of the coordinate system is the center of the ball when it is at rest. The ball was pushed down on the trampoline. The distance the center of the ball's mass was pushed downward, the stretch, is found here, a distance of 0.044 meters. The ball was released and ascended to a maximum height of 0.061 meters above the origin. Using this data, I used the energy principle to solve for the spring constant. The initial state of this system is just before the ball is released, while the final state is when the ball is at its highest point with a velocity of 0. The only non-zero initial energy is spring potential energy. The only non-zero final energy is gravitational potential energy. The only unknown is K sub s. Solving for this yields a value of 105.37 newtons per meter. I used this spring constant to observe the motion of a bouncing basketball, shown here. Note that the footage is sideways. With the choice of coordinate system placing the origin at the surface of the trampoline, I will prove that the coordinate orientation does not affect the experiment's findings. The ball falls in the positive x direction. I will use the data that I know with the energy principle just as I did with the pool ball footage. In this case, the only unknown is the stretch experienced by the trampoline. Any compression the ball may undergo is neglected. Solving for S, I found that the trampoline stretched 0.205 meters. I also created a computer model that simulates the basketball bouncing off of the trampoline. Initial conditions are set here. Note that in the computer model, the ball will be falling in the negative y direction. The motion was simulated using 2 while loops. The first simulates the ball in free fall before it contacts the trampoline. In this case, the only force acting on the ball is the weight force. Air resistance is neglected. The object's velocity and position are updated with Newton's second law. When the ball reaches the trampoline, which is represented in the computer program with a spring object, the while loop breaks. Note that the only energies present in this situation are kinetic and gravitational potential. These are plotted in the loop on a graph of energy change. When the ball reaches the spring and the first while loop breaks, the spring force is added into the net force. Here are the spring's initial conditions. Initial spring length is set to equal the distance the spring stretched in the experiment, and the spring constant value found using the pool ball is input. Note that the spring potential energy is in effect now. Here's my second while loop. With each iteration, spring displacement or stretch is calculated. Using this, spring force is calculated and added with the weight force to find net force. This is then used with Newton's second law to calculate the ball's velocity and position. Energy changes are plotted in this loop as well. Here is a portion of the computer model of the situation. The trampoline is represented by a blue spring which is placed at the origin. Here is a plot of the position versus time of the experimental and predictive data. There are noticeable discrepancies. First of all, the position generated by the computer model dips into the negative y range at its lowest points. This could be because of an imperfectly coded program. The model may not accurately account for the stretch of the trampoline and the compression of the ball. Also in the experiment, the ball only reached its minimum y position once, when it made contact with the trampoline, while the model predicts that the ball would actually reach a minimum twice in the same amount of time. So why do these discrepancies exist? This is not a perfectly designed experiment. Tracker data of the basketball's motion may be inaccurate. Also, the trampoline in reality is not a single spring, but a collection of several smaller springs arranged in a circle. Because the trampoline is quite wide, the actual spring constant may vary at different points on the trampoline's surface. The fact that the weight of my body was also on the trampoline when I dropped the basketball could have also affected the spring and thus its motion. Finally, my code may not be perfectly representative of the experiment. This plot graphs the changes in energy over the course of the experiment. Note that there is no spring potential energy, in green, until the ball makes contact with the spring. After the ball hits the spring, individual energy changes are periodic, but total energy, in yellow, does not change throughout the experiment. Because of this fact, the situation satisfies the energy principle. Total energy change, the sum of changes in each individual energy, is zero. This is because no work is done on the system. Finally, as an exercise in extremely unrealistic physics, let's consider what would happen if the basketball's mass was equal to that of the black hole used in Lab 3, 9.7 times 10 to the 34th power kilograms. Let's imagine that this takes place in a parallel universe where the only two objects that exist are the basketball and my trampoline, and there's a universal gravitational constant of 9.8 that pulls the ball toward the trampoline. If the ball was dropped from the same height that the basketball was in the experiment, and if my trampoline was invincible and could be infinitely stretched, the energy principle tells us that the ball would stretch my trampoline a distance of 1 times 10 to the 17th meters, or 6.23 times 10 to the 13th miles. This distance is about 675,000 times longer than the distance between the Earth and the Sun.